Hello, can everyone hear me? Sounds good. Good. Okay. So, welcome to this evening where the Gothenburg located companies Zenseact, Heart Aerospace and Smart Eye will give you more insight into their products and the cutting edge technologies that you might become part of in making real. My name is Malin Häglund. I work as a product safety manager here at Zenseact, and I will be your host this evening. So, what do these companies have more in common than being located in Gothenburg? Well, in being a safety manager, the first common denominator I come to think of is safety. It's easy to say that you want safety, but how do you actually achieve it? Within the aviation industry, the question about when the operation is safe has been a super important question from the very start. Flying is a complex task by itself and becomes even more complex when you also need to be convinced that the operation will be safe before you fly off. Also, the first time. Within the automotive industry, it's been a bit more easy to argue for safety. You have a driver and you remain on the ground. So, as long as the driver is alert and can control steering and braking, you should roughly be safe, given that the surrounding is safe, which is not always the case. So, big disclaimer. Still, if you remove the driver, the task of knowing when the operation is safe for this autonomous driving system becomes a lot more harder to argue for. And that is something Zenseact presenters will talk about. We also know that the driver is not always alert. And safe operation of vehicles and airplanes can be improved a lot if the driver is assisted with functionality that keeps track of the driver and ensure he or she stay focused on the driving task. And this we will learn more about from Smart Eye. We will start off with Zenseact presenting, and then in the end, when all three companies have presented, there will be a Q&A session. If you are joining online, you can post your questions in the chat during the presentations, and then Louise back there will help me to keep track of the questions. But yeah, we'll start with the Zenseact. So warm welcome to my colleagues Fredrik Sandblom and Kristoffer Pettersson.
Hello. It's great to see so many. And I get the light straight in my face. So my name is Fredrik and this is Kristoffer. And we wanted to talk about safety and AI. And we've got 15 minutes. So we will not fully disclose how we make the vehicle safe in that time, because it's a little bit complex, but we want to frame it and we want you to understand how we can approach the problem and why we believe it's indeed solvable. So when you hear the click, you press the mouse button and then it goes to the next slide. Excellent.
Autonomous.
We're trying to make automated vehicles here at Zenseact. That's one of the things we do. And it's, we say we want to go towards zero faster. So traffic safety is indeed a large part of our goal, why we exist. But automation has a lot of different consequences with it when it is introduced in society at large. And right now we want to focus on the complexity of that task. Because when you are driving, not only do you have to respond correctly to the environment and things that are happening, but you have to do very complex things. You need to understand how the scene is about to develop. in order to predict where others are heading, and you need to be able to compensate for their mistakes. And this is something that is typically extremely hard to capture in rule-based systems. You can always make up a rule, always stop at the stop line, but if there comes a rescue vehicle, you might have to move. You should always stop if there is an accident. Unless you're in the way of something, then you need to move to the side. So making that balancing is very difficult. And we are saying that when we replace the human in this role in the vehicle and the traffic system at large, at some parts of that information chain, we need to have quite, I wouldn't say human intelligence, but we are replacing a human, so we need to have the capability to achieve at least on par performance with human intelligence. And that's the connection to AI that we will talk about in the middle here, and then I will wrap up the safety parts of that. I like to show just some simple pictures here. And I'm claiming that the current level of traffic safety that we have, and now I moved from system safety to traffic safety, it is the result of a gradual evolution in 3 areas. So this is the fatalities per driven kilometers in Sweden. It's not representative for the world, but you can see it was very high in the 1950s, and then it went down, and now it is very low. If you look at the quantitative part, it goes up a lot when traffic increases, but this is per kilometer, so it wasn't so many in the beginning. And why did this go down? So in the very early times, we focused a lot on infrastructure and making better roads. And we did that for quite some long time, and we have gradual improvement. When you build a new road, you build it better than the old one, and you analyze intersections to understand that it should be visible for drivers, etc. And the vehicles have had a similar journey, although not as long. The Romans built roads that still are here, but we've built cars for 100 years that is also safe, and we make them better. Every time you buy a new generation, it is better than the other one with respect to not breaking down, keeping you safe in crash situations, helping you read the scene. And the driver, similarly, we improved our capabilities. I have an old friend, he's dead now, but his name was Olle. And he joined in the 1920s, his colleague or a friend to the city to get his driver's license. And he had never driven a car, but when his friend had gotten his license, the tester turned to him and said, "Shouldn't you do this as well, Olle?" And he said, "I've never done it." And they coached him through the block, and then he got his license. And I don't think he had any accidents, but he learned on himself after that. And the point of that story is only to say that we gradually improved the standards of the driver license as well. So what we do now then, this was a slow process, so 100 years maybe. And the roads also have improved quite slow. But and the tests also a little bit got better and better. But now we replace this, so it's like the tortoise and the hare similarity here. So we want to remove the driver in one stroke and do something in which we have experience from this area to replace the driver. And that is a disruptive change to the whole traffic safety area, we believe. So how do we do that? We have to be quite smart.
How do we do that? Exactly. What do we need intelligence for? So I think everybody agrees that in order to at least drive as well as a human, we do need that autonomous driving system to be intelligent in some form. And we really need it to perform this map from sensor data onto driving. Right? So humans would use primarily their eyes, and then we would use our brain to map that sensor input onto steering and acceleration. And we want to do something similar for our autonomous driving software stack. Though we have maybe cameras and radars and LiDAR, we want to perform this map such that the resulting driving is as safe and comfortable and efficient as absolutely possible. And the key question is how to design this map, how to develop this software stack. So of course this design search space is basically infinite. One very common way that you would find in the industry today is to sort of slice up the problem into different components, which is easy to understand for a human, that you would have, for example, from a camera, you would have a frame, and you would try to detect all the objects, all the vehicles and pedestrians in that frame. You would send those detections to some tracker. Then you would estimate the velocities of the different road users. And based on that, you can do some kind of prediction of where they would likely be in the next few seconds. Based on that, you can then do your own ego motion planning. And then you would control with respect to that ego trajectory, and finally output that steering and acceleration commands. So another key question in terms of design choices is, to which of these components would you use deep learning? And so 10 years ago, no one was using deep learning for anything. These days, everyone is using deep learning at least for this first detection component. So this would be that you have an input image, then you would typically have a convolutional neural network that would then output detections. So this could look something like this, that in this video, each individual frame is processed by a deep neural network that then outputs these 3D bounding box detections, sort of indicating the physical position and dimensions and orientation of the objects. And in a similar way, we can also, for each image, detect all the lane markings, road edges, barriers, drivable free space, basically any kind of information that you would need for the driving task. But given the recent incredible progress in AI, I think it's natural to ask the question of why not use deep learning to solve a bigger part of the driving task? So the kind of design that we're currently sort of investigating and developing that we find promising is to really use deep learning for a bigger part of the problem, to sort of solve perception and tracking and prediction sort of more end-to-end. So then we would, instead of individual frames, we would feed in sequences of sensor data, and thereby enabling the network to also reason around the sort of temporal aspects, such as the velocities and dynamics and driver behaviors and intentions and stuff like this. So that also enables the network to perform these more advanced tasks. So not only detection, but also tracking and predictions. And this, so in terms of network, you could still start off with something similar. You would still sort of encode an image, a single image. But instead of directly decoding detections, you would instead transform or lift those image features onto some 3D feature representation that would actually be common for all the sensors. So here sort of illustrated as a sort of ground plane bird's eye view feature representation around the ego vehicle in blue here. And if you would have other cameras, you would also encode them and lift them to the same common 3D feature representation. Same if you have a radars or lidars. And then you would do some deep learning, sensor fusion processing that would actually fuse these features into one single representation. But we also want to do the temporal fusion inside the network. And the way we do that was we pull in the corresponding feature maps from the previous time steps, stack them together, perform some deep learning temporal fusion processing, and then you end up with this sort of final temporal and sensor fused feature maps. So this guy now contains information from all the sensors and also from from the previous time steps. So it's from this feature representation that we then decode not only detections but also tracks and predictions about where the future behavior of all the other road users, but also make proposals for our own planning or for our own trajectory. And then we would feed all this into a planning block where we would do all kinds of safety checks and optimizations for safety and comfort and efficiency. And for example, if these planning proposals generated by the network would pass all these safety guardrails, well, then we would really be driving sort of with deep learning end to end, but always in this very safe and controllable way. That's how we do it. Mm-hmm. So you're
I'm up next.
Can continue? Yeah.
Thank you. Let's see if the clicker. We fixed it. So we started out by saying that we are trying to fiddle with something that will cause a disruptive change to something that we value quite high. We're happy we have a safe traffic system. And then you show that we use methods that will really improve this, how we can understand the scenes and make those predictions. But then again, we don't fully know how these methods, we know how we develop them, but they are too complex to analyze once they're trained. So we know by experience that the output of these systems is not always fully reliable. ChatGPT can lie to you very convincingly, and we have seen that sometimes networks pick up the wrong features from training data. They've been known to become racist and gender biased, etc. In some infamous examples. So we of course want to avoid that, but we still need to. We believe that it's crucial that we learn how to leverage this in our vehicles to get the intelligence part of it. So it's about bounding and framing. So if we generalize that question a little bit, how do we know that we don't have unreasonable risk associated with using these components, and we take one step back to the vehicle, it becomes the same thing as showing the safety properties of a vehicle, that it's operating safety, both as a system and from a traffic safety perspective. So we'll focus at the end a little bit about that task. And we should start by saying that showing that an automated vehicle is safe is an incredibly complex task. And I think that's the first takeaway that we wanted to give you from this part of the presentation. And then we can discuss afterwards exactly what that means in detail if you're interested. But the first important, or at least I believe it's important, realization that I want to give you is that it's two different things to design a safe system and make it, and to prove that it's safe. Do you agree? Some are nodding. So everybody put up your hand. Is there a difference to those two tasks? If so, then take your hand down. Yeah, so I want to talk to you afterwards. Not because I really want to know how you think here. But the idea is that once we've made a system that is going to perform on par with a human, and humans are extremely good at driving, it's very hard to show that that property exists. You probably have friends that you have been riding with for a long time, and they never caused an accident with you in the car, so you would assume that they are safe. But are all your friends safe? Are they better than the average driver? Statistically, some of them are probably worse, and it's hard to know. So there is a paper that it's almost 10 years old now. It's called the billion miles problem, or it's defining it. And they're stating that if we want to test these systems the way we typically in the automotive industry tested our cars and made them better and better, it's that we test them and then it feels good and we see that there is an absence of errors. If you want to do that and become as good as a human, you would have to drive, is it 275 million miles with no accidents, I think. So if you translate that to having 100 cars that are dedicated, driving 24/7, and you don't have any problems at all, no accidents, it would take you 12 and a half years just to prove statistically that you don't have any problems. And then you have a version that is very old. You would probably not be happy if you bought a new computer and you can run software from 2010 on it. So we can't do it that way. It's not compatible with having frequent updates and feature growth. So we need to shift it a little bit. And the third thing to take away from here is that we need to do it in advance. We have to predict with confidence that the system will be safe when put to use, because we can't let the customers drive with a system that we don't know or haven't shown is safe. So there are a lot of things to say on how to do that. And it comes down to design patterns and making analysis using to partition it, a little bit like how you structured it. But instead of digging into the details, I wanted to show you what a risk acceptance criteria could look like, or what is useful. So this is from how I see it right now. And the world is kind of agreeing right now in standardization and legislation on what we should require from an automated driving system. But I think it makes sense to say that we should make the world better when we put it there. The existence of the automated vehicles shouldn't increase the number of accidents. And to do that, we need to have a quantitative criteria to say that we will have fewer accidents than what humans had when they were doing the same thing at the same place. And secondly, we should also be good at what we intend to do. So we should specifically train on the things that we anticipate will happen, and we should mitigate all the hazards we can understand from the system. So this is about making a good system for the task intended. And thirdly, the residual accidents that happen should not be easy for humans to avoid, because I think that people would find that hard, even if they are few. If they were obviously easier for a human to handle, that doesn't ring well, that doesn't sound good. And the fourth part is to be fair, which relates to checking your data sets so you don't have weird behavior, and knowing that you don't, for example, save some people on the expense of others. It's also an important property in the system. But with those, I think you can get quite far. And we think we can solve this problem and avoid the billion miles problem. And we can do this by getting statistical data from our fleet of vehicles when they are driving, but not closed-loop driving with automated driving. So it comes down to understanding the context they're driving in, testing certain parts, and getting open-loop data for other parts, and then have a rational claim where we can say that if we put it together in a structured and analyzable and correct way, we can argue that the system, when put together that way, will be safe with respect to the criteria that we identified. It's a crucial task, not least to be safe, but also to integrate intelligence we might not fully understand, but it is doable. And the final thing I will say is to explain this picture. I think it's three major tasks that you're doing. You're balancing it at the same time. So it's like a juggler trying to do all of this. But I put the evidence on top, because the evidence is what it is. When the world is telling you how your system is performing or your components, you can try to improve it, but you cannot pretend that you got other data. So it's dimensioning. But you can structure your arguments, the rational claim, why will this work when you put it together? You can be creative here and you can come up with new ideas. And then you can change your design to make sure that you're implementing it that way. And then design it such that you have observability for the things that will back up your claims here, and that's what we call evidence. So you're doing all of this at the same time, and I used our logo here to be kind of circular. And if you try to isolate them, if you try to solve one task at a time, the likelihood is quite large that it will not fit together. So that would be maybe the final comment then. Be aware of your context, because only then we can find the data to actually prove safe driving. I think that's our last slide. Did we make it?
Thank you very much. I don't know.
Thank you for this presentation.
Thank you.
Now we will turn focus inside the car, where the normal use case still is that there is a driver present, at least physically, but not always mentally. And that's where Smart Eye's product can save lives. A warm welcome to John Finnear, who's getting his headset on. Welcome, John.
Thank you. So, excuse my voice a little bit. I have some sore throat. So, my name is John. I'm the chief engineer at Smart Eye. I have worked at Smart Eye since 2010, and at that time we were 16 people at the company, but now we are over 300 people. 160 at our office here in Gothenburg, across the river at Järntorget in this new Wave building. Maybe you have seen it. So how do I switch the slide here? Is it the green? There we go. Yeah, so I'm gonna talk about safety also, because our product in itself is a safety product. And I'm also going to talk about what challenges do we face when we try to develop our software, and what problems do we need to solve? What is our biggest problems? So our main product that we have now, there is cars rolling on the roads having our system in it. We are the market leaders on the driver monitoring field. And this is the simple concept is that there is a camera within the cabin filming the driver, and we want to monitor the driver. So we want to figure out everything that we can based on an image. What is the driver doing? So the basic signals are like head tracking, like how is his head rotated, eye tracking, where is he looking, and then also like blinking, so we can detect the eyelid and if he's falling asleep and things like this. And yeah, we can discover if he's distracted based on where he's looking. If he's not looking at the road, then he's distracted. We have a lot of other features as well, such as like joining and talking and Face ID, who is the driver. So basically anything that you can discover from the person by looking at the person, we try to discover with this camera system. And this is primarily a safety feature for the distraction and so on. So it can be used in, well, the most obvious ones are, is the driver becoming tired? So we can analyze the behavior of the driver, his blink behavior and joining and so on. And we can discover before he falls asleep, how tired is he? Is he becoming more and more tired? So a lot of you probably recognize this coffee cup that shines up. We can do a very advanced analysis of the, drowsy level of the driver, and also distraction and so on. And sometimes where this is useful is, for example, if in the future we have automated driving, and you the car needs to hand over the drive to you, then the car wants to be certain that the driver is actually attentive. He's not sleeping when you hand over the control to the driver. But today the driver monitoring system is also a safety feature, not only for automated driving, but currently when you're driving yourself, if you're falling asleep while driving. So this is used in a lot of the. There is regulations coming, Euro NCAP and so on, that will require this kind of systems in the future in order to be classified as a safe to drive car. So that is like the most mature technology. But what is coming more and more in the future, and the industry is talking more and more about interior sensing also, like cabin monitoring. And then, for example, if you have a camera located at the rear view mirror with more of a wide field of view camera, so you can see the whole interior of the car, not only the driver, but you can see the passengers and the people in the back seat. So there we can do more kinds of detections. So now it's not only what is the driver doing, but what is tell us everything that is happening inside of the car, basically, is what our customers wants to know. So we can detect the body pose of the driver, like the full body, because it's not zoomed in into the face. We can detect seat belts. We can detect objects in the car, like a wallet, if someone forgot a wallet or a bag. We can detect a child seat. We can detect the children. So, for example, one use case for a child seat is if it's in the front passenger side and the airbag is armed. That's dangerous because usually you want to turn off the airbag if there's a baby seat in the front seat there. So it's coming more and more safety features based on this technology also. It's not yet rolling on the streets, but it's coming into the future. So what technical challenges do we face at Smart Eye in order to solve all of these problems? Because this is complicated algorithms. It's state of the art. Like we are doing a lot of innovation in order to solve all of these technical problems. We're the market leaders in the world on this technology. So we have to always innovate to be on the top. Traditionally, like 2010, all of our algorithms was computer vision. The company actually started in '99, so we've been doing head and eye tracking for a very long time. So then everything was computer vision, but as the previous speaker spoke, neural network is becoming more and more used within computer vision and so on. So gradually, more and more of our algorithms is based on neural networks, and I would say about 70% now is neural networks based. But we also have a lot of math in our problem. So we have like linear algebra, nonlinear solvers, just the optics of a camera optics and so on requires a lot of math. So another major challenge for us is that we're working in the automotive industry. So since we work with a lot of different OEMs, we have a lot of different platforms, hardware platforms that they're compute platforms, and they have different operative systems, there's different ARM cores, QNX cores, and so on. So we need to be very platform agnostic. So we need to write our code in a way which is very platform agnostic also, with only a thin layer to, handle the different platforms. And within the automotive industry, there's a lot of safety standards and regulations. So we need to write safe code with high quality, and we need to prove that it's quality. And our development processes need to be of high quality as well. So there is standards such as ISO 9001, there's SPICE, there is ASIL, there is different kinds of standards that we need to fulfill. And also, since we have so many different platforms and the way we test our algorithms is based on videos, like cameras, is video based. So that's very heavy processing wise. So we need to have a very rigorous CI system, like automated testing system, and a very big machine park in order to be able to test all of our algorithms for different platforms, different cars, different positions in the cars, different cameras of different quality and so on, and different lighting conditions. So for each customers, we need to basically prove that yes, we fulfill your requirements with our algorithms based on your videos and your cameras and so on. So that is a big challenge for us. And all of this, of course, generates a lot of data. So we spend a lot of time on collecting data, annotating data, and storage is starting to become a problem as well, because we have petabytes of video data, and we need to be able to process this video data. So like it's a lot of requirements on big data, and we use the data for the training of our algorithms, but also for the validation of the algorithms and the signals, and it's not only validation as a one-time. Each customer wants to make sure that the algorithms works on their camera in their car at that position. So what technology do we basically use, or what competences do we need at our company to solve these problems? So we work a lot in C++, embedded C++. We need to be writing very fast and efficient code to run on these cheap platforms, hardware platforms that is in the cars. And a lot of the neural network and so on is done in Python and scripting and so on. We have a lot of machine learning, a lot of computer vision, data acquisition and annotation, and good knowledge of the embedded platform so we can optimize for each platform. And a good knowledge in camera-based hardware is also useful. We have other business areas as well. our major business area is the automotive industry and being in real production cars on the roads. But we have also aftermarket product where we develop our own camera that you can just place in your car. If it's not built into the car, you can just have a driving monitoring system in the car. This is useful for more low volume products. For example, if there is a truck fleet that it becomes regulations that you need to have a driving monitoring system in trucks, they can buy an aftermarket product and put into older trucks to still have a driving monitoring system. Maybe the company wants to monitor their truck drivers so they drive more safe and so on. We have also a segment which is assistive technology, where people can control things with their eyes and so on. We have research systems that do behavioral research and in universities, or when you want to analyze driving behavior on the roads and so on. And we also have systems for flight simulators and car simulators where they want to evaluate, okay, based on this situation, where is the test pilot looking and things like this, doing analysis of that. So we have a demo station located over there. It's a screen and a camera, so you can just walk up to it and it will start tracking you and show you where you're looking and how your head is rotated. We have colleagues which will be standing there and can show you and ask questions, and if you have technical questions, feel free to talk to us. This will be after the presentations. Yeah, I think that's it from me.
Thank you, John.
Thank you.
Now we will leave ground and let Heart Aerospace presenter Andy Larkman talk about proper risk handling and verification challenges you need to cope with when you want to make electric air travel a reality.
I've been flying for over 20 years and test flying for the last 10, during which I had the opportunity to fly more than 50 aircraft types. I'm lucky to be one of the few who gets to fly some of the world's most interesting and advanced aircraft. But what we're doing here is the coolest thing I've done, and I'm so excited to be involved in the development of electric aviation.
Everyone, it's my absolute pleasure to be here today to talk to you. I am Andy Larkman, the Chief Test Pilot of Heart Aerospace. I'm here to kind of connect to the previous speakers, looking at how we actually use this emerging technology for our data gathering and analysis, and how we apply that to some of our specialist equipment in the air. To get through these testing, obviously we need to be quite experienced. So my background is actually, as you can see, in the military initially, and technology, like me, has advanced a little bit over the years, and I spent about 20 years in the military. The first half flying operationally maritime patrol airplanes, surveillance aircraft, which of course had a lot of technology. I then became a test pilot, graduating from the French test pilot school on exchange. Then I moved into specializing in heavy aircraft test. I've been a civilian now for about 5 years, and the last 2 years of that I spent at Heart Aerospace. Really lucky to have flown, over 3,500 hours now, and I think I'm getting near 60 different aircraft types, thanks to adding a few additional ones here. Enough about me, I guess. Aviation, Gothenburg. Any ideas where maybe Gothenburg started? Well, here it is, 1938. The shipbuilders actually, they had a go, and they built this Götaverken GV38 aircraft. And I have to say they did a great job, because it's actually still flying today, and I had the pleasure to actually fly it, making it the oldest aircraft I've ever flown. And I really hope one day we get the chance to fly it alongside the newest aircraft in the Gothenburg area, which is what we're developing. It's the ES-30. It's a 30 passenger hybrid electric aircraft. It's the only brand new large class airplane actually being developed and certified in Europe, and we believe actually the entire world at the moment. So we really are pioneering this. So it's obviously not just me. Who are the people behind this? Well, Heart Aerospace, it was actually founded in 2018 as a research project, and then it just grew and grew. It is a Swedish company. It is based here in Gothenburg. We have our headquarters at Semcon, just down the road. We also have our hangar with some of our testing facilities up in Säve airfield nearby. As I say, the company's grown, and we have many investors and partners now. A couple just to highlight, we have Breakthrough Energy Ventures, which were actually from Bill Gates, and more recent investors such as Air Canada and homegrown Swedish aviation itself in Saab Aerospace. So before we fly, we have to test, just like you saw in the automotive industry. You know, certifying aircraft, it's hugely complicated. A theme we've heard already today, and we have a lot of work to do to get ready for that first flight, and it takes quite a few years. And I think someone asked me earlier, why do we have test pilots when the aircraft's not going to fly until 2026? Well, you know, we're already engaging and supporting in the design phase, helping with things such as designing the cockpit, my office. We're advising on the safety engineering, and we're helping to develop things like the flight control systems, which are very important for the handling of the aircraft. And we're already starting to develop our very comprehensive flight test plans. We're doing this at the same time as actually we're establishing a brand new cutting edge flight test center here in Sweden. We're doing all this so that when it comes time to test, we can execute those complex test procedures in an efficient manner. So we can analyze the huge amounts of data and then package all this up into the evidence that it's required to give to the regulatory authorities and actually certify and prove the airplane is safe. But you know, despite all these challenges, you know, test and certification, it is essential to the safety and reliability of aircraft. And it's on us as the aviation industry to keep pushing the bounds of this and make sure that it's safe for you as the passengers. So what do we do with the flight test? There are many phases to go through, and I unfortunately don't have enough time to talk about everything on the slide there. But the main key focus is that, you know, like I said, it's complex. We have something like 30,000 individual test points to perform, an average of between 5 and 6 minutes per test point. The aspects that we're looking at when we do these, firstly, is safety. We're looking at the performance of the aircraft, how it handles, how the systems interact and work with each other on board the aircraft, and how reliable it is. And then finally, we then have to show the regulator, which is EASA, that the aircraft is compliant and safe. We do this through our testing approach. It's not just a case of me, the test pilot, jumping in and having a go and being amazing. In fact, it's done very safely. We have a very specific approach to how we do this, and a cycle, as you can see on the bottom of the slide there, using a combined team. We need to look at all the requirements. We need to analyze those and then plan each individual test sortie, starting from the ground up. So we start with rig, ground testing. We build up to the first flights. We then expand the envelope of the aircraft, taking it to the edges of its capability. While we're doing that, we're looking at the systems, the avionics testing, and then we're actually starting to bring the certification testing in an early stage, having the regulator riding alongside us as we do it to get towards that certification approval. And as I said earlier, you know, we've got 30,000 plus test points to organize, problem solve. So we need a very robust data management system that's gonna help us do that. And that's where we're using the same technology that the guys were talking about earlier to create that system in-house to make sure that we can fit every possible bit of data efficiently into every test sortie, so we can then analyze that, sometimes in real time during the flight, and I'll show you some of that later, then store and ultimately report on all that data. So what about the aircraft itself? So we're going to use prototype aircraft. We have flight test instrumentation. This is the specialist equipment that we use as testers and put on board the aircraft. Again, I'm not going to take you through the slide. Just to say that we need to prioritize the safety during all of these flight test sorties. And we actually have to conduct a lot of different tests. So we have more than one prototype, all configured in different ways to do this. This is a kind of an example of the first prototype we're going to have. It have a lot of the complex equipment fitted to it, and I'm just going to take you through some pieces of that equipment and explain in more detail. But I have to say, actually, it's not just the aircraft that gets modified, but actually the pilot ourselves, we get fitted with all sorts of flight test instrumentation as well. And I do remember John talking there about aviation. I have actually done some flight tests with the same technology that Smart Eye are using, and I can really attest to how beneficial it is to us when we're doing testing. I actually used it when I was doing some testing for nighttime tactical landings in transport airplanes. Just as an aside, you might notice there's a lot more orange appearing in my presentation. Everything flight test is orange. Sometimes we even wear orange, so you'll get to see that through the rest of the presentation to depict what's actually flight test and what's normal aircraft. Before we get into equipment, let's talk about the team. So we've got the FT, the flight test engineer. He's at the core, actually, of the testing. He's there to look through the test risk, working alongside the pilot, develops and executes the test plans. And, when we land, he may be on board the aircraft, for example, or on the ground, then has to evaluate everything and then report on it and problem solve. Assisting him, we have the flight test instrumentation engineers. They're the guys who actually source, design this equipment. They install it, they have to calibrate it, they have to constantly monitor it, adapt it, maintain it, and then also report on it for the regulators. And of course, we have the test pilot. We're there to support the flight test engineer, do what he tells us, fly all the test points, but really, make sure we've got good safety of flight when we're doing the testing. And then it's really important that we have a robust method of reporting the feedback once we've done the testing. So every person on that crew plays a very vital role for the aircraft development, but it's not just us. We've got an entire team on the ground supporting us. What about the actual equipment? So let's talk about truth data to start with. How do we know the aircraft's going the speed it says it does? Well, we don't to start with. So we have things such as the pitot boom here. So this actually sticks out in front of the aircraft, away from any disturbed airflow, to give us accurate readings in speed and angular data. We can also do it at the rear, and we have a trailing cone gets wound out from the back, and that can also measure. But we have all these domains in the company who need to come together to help us do that. Another great system for flexibility for us is the ballast system. What we can do is, while in the air, we can actually move water or even fuel from these tanks from perhaps the front to the back or left to right in the aircraft, allowing us to change the center of gravity and the balance of the aircraft for when we're doing specific test points. And it allows us to do it quickly without landing and changing and having to use old-fashioned sandbags, of course, in orange. Getting a bit more exciting now. Quite a dramatic looking test point there with the sparks flying from the aircraft. This is something we have to do. We have to see what the minimum speed the aircraft can actually get airborne. And of course, I don't want to damage the aircraft, so we fit the tail skid to the back. The tail skid itself is also heavily instrumented to allow the pilot to perform the maneuver safely and the engineers to analyze that data. Kind of building up, getting a bit scarier now. We test the aircraft to the extremes, so we have to have a means of saving the airplane. So we use the tail chute or the spin chute. It's a device you can see circled there in red at the back of the aircraft. The idea is I lose control of the airplane. I can deploy this drag device, and you can see there's a NASA research airplane there on the right, showing how it's now suspending the aircraft. Then what we do is we then cut it away, allowing the pilot to regain control of the airplane and survive for another day. Not always the case. Some airplanes, you may have an ejector seat, which is great, but large airplanes we tend not to, so we need to figure out a way of letting the actual crew escape. So we fit bespoke escape systems and blowout hatches on the aircraft so that we can provide a safe means for them to evacuate during some of those high-risk test flights that we do. So let's have a look at an example of how all this will kind of come together. I'll just take you around this slide first so you know what's happening. So this is a flight test instrumentation trace from the ground station. So there's a still there. Up here we've got some information about where the flight controls are. The green is actually the stick, so that's the center position, and this represents the pedals. The pilot already will have the controls set in a manner to deliberately put the airplane into a spin. It's an Alpha jet, which is a fighter jet trainer. It's got a pilot in the front, a flight test engineer in the back, and we do have ejector seats, which is nice. On the top, we've got all the engine instruments and some extra data about the mass and the fuel on board, center of gravity. The main thing we're interested in for the data is here. These are all traces of control positions and, of course, the pitch, the roll, and the yaw of the aircraft. And we analyze what that's doing in the spin and what happens in the recovery. But my favorite bit is over here. This is the altitude bar, and this will come down as we fly, and there's different colors. And as the pilot, I'm in the cockpit, and I know when I hit these altitudes, I have certain actions to make. And the best one is definitely at 10,000 feet, and all I have to do is pull the handle and use my exploding chair to save myself. Thankfully, never had to do that. And it's not just us on board, like I said. We've got the telemetry people helping us on the ground, extra safety pilots helping monitor me, air traffic control, rescue services on standby, and quite often we have the media there watching as well. So let's see what happens. Test crew preparing. This is the test pilot in orange. External cameras watching the spin develop. And the pilot's now fighting with the controls, trying to get it into a nice smooth spin, being taught into what he's doing and trying to count how many times he's going around. Then on the ground you can see all the data now starting to appear on the screen and the altitude going down. Then the pilot puts in the recovery actions, and hopefully the airplane comes out of the spin without too much trouble. So you can see there's quite a lot that actually gets put together to test these airplanes, and they don't look anything like what you'd imagine a passenger airplane to look like, for example. So, to safely and efficiently bring a new aircraft to the market, it's hugely complex effort, like we've been saying, and it does require a lot of emerging technologies. But more importantly, for us, it's not just about the technology and the test crew doing that job. It's actually about the whole entity. And for us, in our company, it's actually really important that every single employee has a part to play in the safety. And that also comes with the development of a company-wide safety culture. And that's ultimately what's keeping us safe in the air. And this is why having the right people, at the center of our program is so important to us. Today we have approximately 200 people from about 30 different nationalities, with so much diversity and experience, proven track record of building regional aircraft, people from other industries with experience of electric vehicles, and of course bringing startups all the way up to industrialization. However, to make our aircraft a reality, this is not enough. And in fact, we need to expand that excellent, diverse team. And that's why we want to share our vision with people like you so that you can come and join us. And if your phone's not as good as mine, of course, we'll give you an opportunity to come and chat to us later. I'm just going to leave you with some final words from our very own flight test instrumentation engineer, Guilherme, and in fact he's here with some members of our team, and we'd love to take some questions or conversations with you after the presentations. Thanks very much.
And now I would like all presenters up on stage and see if we have any questions from the audience. There is one question. Wonderful.
Hello. I have one question for Smart Eye, or maybe for Zenseact. So, for a safety critical system, the driver monitoring system is crucial for if we can activate AD or not, because it tells the system what's the status of the driver. Then it's kind of probably a arguable ACOD component. But then you have only one camera to look at it. How can you make it ACOD if it's ACOD?
So currently the highest level of ASIL that we have is ASIL B. So we don't have ASIL D. But was there something more I can answer with that question, like handover or questions like that from automatic?
And the question was a bit also for AD driving, right?
Yeah.
It will raise to ASIL-D if you're supposed to guarantee that the driver is there to, or
Yeah, so we have different parts of our software has different ASIL requirements, and we have some FUSA and also quality QM. This is not my expertise, so I don't know if I can answer the question correctly. But yeah, I can't give you that answer. Maybe you have something you can say about this?
I'm thinking hard. So you mention a special case where you have said that it's ASIL-D important. You won't have that kind of risk reduction measure upon the risk that you don't know that the driver is available to take over. But that would be a consequence of your design, and I would say that it seems unwise to be that reliant on being able to hand over to a human. Maybe you need to if you are flying in the air, but we have other means to manage the situation if a driver is not able to take over. And specifically for automated driving, we are assuming that the driver is not there. So I think it is not, we would not have that decomposition for automated driving.
I think I can fill up a little bit more there, because we are a monitoring system. So like we don't increase the speed of the car or we're an extra layer of safety. So you would have the same safety level as if you have today in the cars without our system there. So we just add, an extra safety on top of them in most cases.
I guess also you could use the seat sensor if you want to know if the driver is still in the car, right?
thanks. Any more question? There is one.
Thank you. I'm wondering about the future, about the legislation, about the law. When do you think we will be able to put those products, automotive products, into the market, and where is the responsibility if something will happen?
Okay, so when will we get AD vehicles?
Or I can start. So, There is a legislation called ALKS that allows you to put vehicles that can drive for themselves without driver supervision already in place in Europe, and a competitor has launched such a vehicle this year. The availability is quite limited. It's useful up to certain speeds in very limited scenarios, but during that time, the driver can play video games on the center display, for example, and don't have to monitor. And the company that is doing it's Mercedes. They are quite open that you don't have to supervise until they have asked you to take over, and that handover is fully taken care of. They will remain responsible. But this is the first legislation that allows it, and it's present in Europe. In US, the scene is quite different. So I would say the path to large-scale implementation of automated driving, we are not there yet. But we can have the first version systems out from now.
Yeah, and from our point of view, we have a safety system that is adding safety even without automated driving. So this driver monitoring system can help you even if you're driving yourself, if you're falling asleep and so on. So we already have cars rolling on the roads today and in production. We already exist and work with a lot of different car manufacturers. So, but in connection to the AD and so on, I don't know if we're there yet. That's more on your side. But in terms of regulations, Euro NCAP is a regulation that basically says that if you want to have 5-star safety car, you need to have a driver monitoring system in your car. There's also regulations in Asia that requires this, and also also legislation from Europe which says that you should have a driver monitoring system in your car. And Euro NCAP, I think, is from 2024. You basically need the system in the car.
Yeah, so aviation, I mean, let's talk about putting me out of a job, right? Autonomous air vehicles, it's still quite far off. And in fact, I would say more work right now is going on in aviation to take one of the pilots away. Because in large commercial airplanes, we have a regulatory requirement to have 2 pilots. So in terms of pilot monitoring, well, that's easy, right? We have another pilot monitoring that pilot. But then when you go into what we call single pilot operations, then we have other aspects we've got to think about. One of the most important is going to be the workload for that one guy. Another aspect is now monitoring, his health monitoring. What if he collapses? What if he has a problem? So maybe more robust medicals in the first place, more robust monitoring, such as monitoring his eyes to see what he's doing, make sure he's alert. Or maybe support on the ground from another pilot, for example. I think that's the first step. And there are studies right now, but at the moment, there's no regulatory approval for single pilot carrying 30 passengers, such as the S30. That's why we've designed it for 2 pilots, but with a single pilot in mind, to make it easy to make that transition later when the regulator decides which technology that we have to use to prove the safety.
Yeah. Okay. We have one question over there, and then we shall also check if we have any questions online. But takes this first.
Hello, good evening. And my name is Williamson from Robot Automotive. I'm really interested to say 3 together because I see it's very much fit. Because I used to also shortly work with aviation industry. I know aviation industry, what is like a driver monitoring system, definitely is relevant for the pilot, I would guess. Secondly, when we come to the system safety, I think the basically aviation is pioneer, have redundancy, triple redundancy, diversified. That's definitely be very relevant when we talk about the autonomous drive. Yeah, we definitely need to support just fair operational. So my question to you is to actually end is that why this electric plane eventually happened in Gothenburg? How about other countries in Europe? Just curiously.
Yeah, I mean, that's a great question, actually. And I think, you know, to give Sweden credit, in fact, the whole Nordics credit, they are actually the people, you know, pioneering the idea of carbon-free aviation. For example, Norway, they've made a promise to go carbon neutral. And actually for our aircraft, for instance, it's not going to solve the problem of flying from Paris to New York. Not right now, at least. But when you look at places like Scandinavia, where it can take you all day to get somewhere that's just 50 miles away, because you have to drive all the way up the fjord and back round or take the ferry. So I think that the need is there, actually, and the willingness to, you know, to actually meet those commitments for carbon zero. So I think that's why Scandinavia is at the heart of it. And also, we have the support of the European Union as well. But we're not just designing this for Scandinavia, we are designing it for the entire world. And there are many use cases all over the world where this product, for example, would be useful. You know, for example, New Zealand is split in two, country with 2 islands, and it take you all day to get from one island to the other unless you fly.
Thank you. It's quite a fair answer. If allow, I just have one more question. And you mentioned actually, Zenseact talk about the develop the autonomous driving systems. If I understood so far, you are not actually approaching AD level 3, as you mentioned, the bands already have a level 3 automated lane driving. So my question is that actually from Zenseact perspective, when do you see this commercial actually availability, of course, to be profitable, also make the older actually ADS related subsystem like sensors, radars, to be price-wise competitive, you need the commercial size. So my question to is a little bit beyond actually what the in the technical side, because it has to be worked together. How do you actually see in the few years this autonomous actually driving or automated driving market, where the main OEMs, particularly in Europe, is heading?
So I guess we are equally well equipped, I think, to answer this question. My first question would go internally. Have we communicated our time plans in this area? Because I sometimes speak more than I should, and I don't want to do it now, especially when it's recorded.
I think we never talk years.
No.
No.
So we have a time plan.
Because it's very much connected to VCC.
Yeah.
So,
if we take one step back to answer that question, we are dedicated to driving automation. That includes both ADAS and automated driving. So technically, we differ between those two. And we have communicated that we see similarities and synergies in developing both of it. So for sure, we are believing that we can do this within a reasonable time frame. And we think that the emergent technologies that we will use, we didn't actually pitch so much the technologies that we do use besides the two particular focuses, but we need a lot of different skills here, but we believe that it's all accessible to us. We can put together an automated driving system now, but it's a tedious job to do it properly and ensure that you do it right. So that, of course, says something about the time frame, but we believe in what we're doing. And we're still getting funded to do it. So others believe in us too. I guess that's the vaguest, but still kind of attempt to answer I can give.
Thanks. Okay, let's see if we have any questions online, Louise.
We do. So let's start with the first question to Zenseact. You mentioned that statistical safety verification is not feasible because of the amount of miles required. Can you share some method names that are more feasible, especially for deep learning?
Well, you can start, and then I can, if you want to do the statistical.
So the statistical reasoning is quite simple. If you want to estimate something to some degree, like one failure per something, and you want to test that with confidence, you need to observe more than that and have still 0 outcomes, right? That's the basic problem. And there is no way really to get around it. There are extreme value approaches or predictive measures where you can try to verify that certain behaviors, if they don't occur, then some other things that you cannot observe to this rate will not occur either. It's called EVT, or extreme value theory. And that is very promising, I would say. But a problem with that is that before you can apply it, you need to verify that it's working for the particular problem that you have in mind, which in itself is a verification task that requires you to solve the original problem of gathering a lot of data. But if you think of generations 2 and 3, and maybe even 5 and 6, then you could argue that you have all the data statistically because you proved that something was working, and you put it out there and you actually get this large number of data. And then you can verify that the EVT predictors are working as well. And this is research, it's not my particular area. But I believe that we could argue that certain similarities are so strong that they would be valid for future generations as well. If you have changed only a few things, and you can argue that their impact on those predictors are minor. So I think that in the future, we can make use of such methods to be a lot faster to verify the performance of the systems or the safety. But in the first versions, that is very difficult, or I don't actually see how you can do it.
Yeah, and so for the question about whether you have deep learning or not in the stack, and how that affects the safety argumentation and the statistical evidence, I would say that depends a lot on what you use deep learning for. So I would say it's no longer a question if there will be deep learning in the software stacks. There's in all modern automotive software stacks nowadays, there are deep learning. But it's a huge difference if you would, for example, only use it for the detection, as we were discussing, or if you would have it to some intermediate step where you would do tracking or prediction, or if you would try to do it fully end-to-end, where you would just have one big neural network that would take in a stream of sensor data and output the steering and acceleration commands. Then you have this really problematic situation that we know that in ChatGPT and other, that if it turns out that input data sample is really out of your training data distribution, then it's really difficult to know what is going to come out. It's really difficult to sort of have to assure safety in those circumstances. So this is one of the reasons why we believe that we should, of course, maximally leverage the power of deep learning and AI, but we must do it in a very safe and controllable way. And this is why we would still follow all the safety standards, redundancies, and also have this additional safety layers or safety guardrails in terms of controllability and safety checks, so to make sure that output is actually reliable. And then it's okay that if there's indication that it's not reliable, it's not robust, it is out of distribution, then it might be that we go down in performance, but we ensure safety in all cases. So that's the way we're sort of thinking about it.
Oh, thanks. Let's take one more question, and then we will also like to allow you to move around here on the different stations. But I think there is one more.
Online, yes.
Yep.
We have a few, but we'll take one question to Smart Eye, connected to the ASIL levels. So can you use Zenseact's hybrid approach, that most of the pipeline in network, for higher ASILs? Don't you have to have some kind of algorithm redundancy?
Yeah, so it's very unfortunate we don't have our safety expert here, but I will try to answer the questions, take it with a grain of salt. There has been argumentations of redundancy, so if we can have multiple different signals trying to say the same thing, like so we can detect the seatbelt based on the camera, but then there is maybe a seatbelt detection. In some countries, they like to put the seatbelt into this one, but they don't have it on top of them. They are just sitting on the seatbelt, for example, to fool the system. So the more different ways you can detect a certain feature adds redundancy. And now here comes the grain of salt. I think that you can argue if you have like multiple different sources, the ASIL levels maybe can it can help with the ASIL levels. But a lot of our customers want to have signals for redundancy.
But it's also that deep learning is very new, and there is a standard that is being developed right now about how to work with deep learning, and they are using ISO 26262 as a basis. So it's a future question maybe to answer that. One last question, and then you can walk around on the demos.
Are car companies sharing any of the big data concerning safety when it comes to machine learning and other stuff like that? Or are we still just working in silos? Like Mercedes is doing their thing, Tesla's doing their thing, Volvo is doing their thing, you guys are doing your thing. Is there any thought about sharing the big data so it doesn't have to be such a...
I guess you know, Christopher.
Yeah, in general, yeah, most car companies and other companies are working in silos. We at Zenseact actually just recently released one of the largest automotive datasets in the world with more than 100,000 frames for training with full set of annotations. And so we're hoping that this will actually contribute both to the research community, but also to startups and other, because it's also you can also use it for commercial purposes. So we are actually thinking in the way of sharing and sort of solving this together with both the research community, but also the startup community and everyone that is interested to work on our problems. Then a great starting point is to start from real data that is coming from the kind of data that we use internally.
And I also would like to add that apart from sharing data, there are a lot of forums where industry is sharing. So if we look really close, we have SAFER, which is the Chalmers Traffic Safety Research Center, where a lot of local partners are discussing pre-competitive questions. But safety assurance for automated driving is such an area right now, so we are sharing knowledge there. And if you extrapolate that throughout the world, you will find a lot of different such forums, and maybe at the end of it, you would have the actual standardization. So when these standards are being written, companies and institutes come together and share their ideas about how would you approach this problem, what can constitute the best practices of industry. So there is a lot of sharing ongoing, but at different levels and at different maturity.
Okay, now if you have more questions to the presenters, you can catch them in the room. And I will let you who's joining here physically to visit the different demo stations. And for you who's joining online, I would like to thank you for joining. And Louise will make sure you get the contact information you need if you would like to join one of those companies. And you can stay here in Aquaman until 7. And yeah, ask questions, walk around here, maybe take some more pizza. And I hope you will have a great stay here. And I thank you all for coming here this evening. Thanks.